Hi, I'm Rehan from Cornell University. This work was done jointly with Chuan, Aoni, and Lawrence from Facebook. Richard Hamming says that the first rule of systems engineering is if you optimize the components, you will probably ruin the system performance. This is true for machine learning model systems as well. What we study is usually an individual model. For example, the left figure shows the transformer, a model that is popular at NLP tasks. The right figure shows the architecture of ResNet, an effective model for computer vision tasks. However, what we build for practice are large systems, such as the self-driving system, dialogue system, and recommender system. These machine learning systems usually include several machine learning models that talk to each other. Each individual models are developed and trained independently because of several reasons. Models are owned by different teams. Models may be updated at different cadence. Models are implemented in different platforms. New downstream models may be added to the system, and so on. In our work, we study a problem for machine learning system. Can improving a model make the system worse? The answer is yes. There is an example in recommender system. Assume a recommender system receiving image classifications as input. Consider a user that is interested in Rainbow Dash. The Rainbow Dash is obviously not a class in the image recognition system. So the recommender system relies on the parrot classifier that can identify Rainbow Dash, because both of them have rainbow color. In the other word, it means that this parrot classifier has a lot of false positives for this user, which works well until the parrot classifier is improved. We further ask, can improving a model make the system worse even after retraining the rest of the system? Consider this learning setting. Machine learning system is a directed acyclic graph. The original feature vector is divided into 3 pieces, XU, XV, and XW. The model U and V process the fed features to output FU and FV. Downstream model W takes FU, FV, and XW as input and produce FW as the output in the end. We assume data space is fixed. The evaluation matrix, including test dataset and loss for each model, is fixed. Everything else can change in between model updates. Models in the system can be updated. An update replaces model V by a better model V prime. If I make an upstream model better and I retrain, all of this is downstream dependencies. If any of downstream dependencies gets worse, that is self-defeating improvement. We analyze self-defeating by the error decomposition. Assume we have upstream model V and downstream model W. We can decompose the error of the downstream model, which is the loss of downstream model minus the loss of base optimal downstream model. The decompositions have 3 parts: upstream error, downstream approximation error, and downstream estimation error. The new introduced 2 terms are the loss of base optimal downstream model given the upstream model, and the loss of optimal downstream model in the downstream hypothesis space given the upstream model. If the error of downstream model increases, one of these 3 terms must increase. The upstream error increases when an improvement in the upstream loss does not translate in a reduction in base error of the downstream model. It can happen due to the loss mismatch or distribution mismatch, which is commonly studied. We are going to introduce 2 examples to show how downstream approximation error and downstream estimation error increase. Consider this simple system. The upstream model is to predict 2D points. The left figure shows the ground truth that how each point should locate. The downstream task is a binary classification problem with green and red labels. The hypothesis is a linear model. We can check current upstream model V in the right figure. Although the predicted 2D points are not accurate, they are separable and linear separable, for the downstream task. If the upstream model is improved to V prime, these points now are separable but not linearly separable. The downstream approximation error increases from 0 to non-zero in this example. This is another example that downstream estimation error increases. The settings are the same. The upstream still predicts 2D point, and the downstream is a binary classification task. The difference is the downstream model is now a quadratic classifier instead of the linear classifier. V prime performs better than V for the 2D predictions. Although both V and V prime provide separable 2D features for the downstream, we need more training data to learn a more complicated classifier with respect to V prime. If training data is limited, like here we only have 6 training points, we instead will get a worse classifier. We show a case study in pseudo-LiDAR system. The first module U takes stereo image as input and generates a disparity map for each pixel. The second module, R, is a point cloud generator. It converts disparity map into 3D cloud point. Then V and W are car detection model and pedestrian detection model. We improved the upstream model from U to V prime by minimizing a more matched training loss, disparity, mean absolute error, rather than depth MAE. This improvement leads to self-defeating improvements in both car detection and pedestrian detections. Average precision 3D and average precision BIV are two evaluation metrics for object detections. Larger is better. We hypothesis for the self-defeating of car detection. Upstream error increases because cars are generally far away. From U to U prime, the close cloud points are more accurate, while more further cloud points get worse at the meantime. We hypothesis in the self-defeating of pedestrian detection, downstream estimation error or approximation error increases because more noise in some point clouds makes it harder to learn a good detector. In conclusion, improving a machine learning model can make a system worse. Self-defeating improvements can and do happen in the real world. Error decompositions can help us understand why this happens. We should study machine learning systems holistically. That's all for the talk, and thanks for listening.